Let's see where we left off at. I think we left off down there with the fluorine compound. Left off here again, we drew one resonance structure of this. Importantly, we're not going to be able to move this pi bond over because we would never leave this oxygen here without an octet. So only one resonance structure of this, and the one resonance structure we drew with the double bond to fluorine, positive on fluorine, that was a major resonance structure. So the hybrid would look more like that particular structure. Okay, the remainder is pretty much miscellaneous, and other resonance structures above. Okay, we mentioned those up here. Being able to draw resonance structures into the benzene ring, but also into other groups that are on the ring, here and here. And there's going to be a big difference between these two compounds, and thus we can then answer questions such as this down here. Again, understanding that this lone pair is in a p orbital, we talked about that during week 1, week 2. And since it's in a p orbital, it's conjugated. Since it's conjugated, we can start drawing resonance structures, and starting with your lone pair is a very good place to begin. There are lone pairs on this oxygen, but they are not in p orbitals. The lone pairs here are hybrid orbitals. You only do resonance with lone pairs that are in p orbitals. Resonance is basically p orbitals conjugated. And the resonance structures are just different structures that illustrate the one hybrid. Okay, the last page is a little bit of acid-base. And we actually looked at resonance when we looked at acid-base chemistry back there in test 1. And you should be looking back at that. And you should understand the pKa's of these different OH compounds. Regular alcohol, a phenol. A phenol is much more acidic than a regular alcohol. A million times more acidic. But then a carboxylic acid. So you should understand this trend. The anion here is just a plain anion. This anion is resonance delocalized into the benzene ring. But why is the carboxylic acid so much more acidic? Why is the carboxylic acid so much more acidic? Right? Anytime we're considering an acid strength, we really want to consider the conjugate bases, right? Which is more stable? This, right? We can draw all types of resonance structures, moving these in, moving these out. Resonance stabilized anion. Yeah? Actually, how many resonance structures can you draw of this structure? How many did we draw of this last week?
3.
3 additional. 3 additional resonance structures you can draw here. No resonance structure is possible here. If you don't understand that, you need to make sure you understand that. There's no resonance here. I mean, the lone pair is here, not even a p orbital. This is an sp3. Okay? 3 additional resonance structures. Over here, we have our carboxylate, which is more stable than this. The pKa implies that. This is more acidic, meaning this must be more stable than this. Why? Well, we can do resonance. These electrons move here, these electrons out, the old N out, and we get boom, boom. We get this resonance structure, right? And that's actually it. We can only draw one resonance structure, one additional resonance structure from here. But here we could draw three. Why is this anion more stable than this anion? The charge is actually more delocalized here. It's more spread around here. Seems like that would make it more stable. Why is this one more stable? Anybody? What type of polarity? What do you mean by polarity? Electronegativity. So further explain. What about it?
The oxygen wants electrons.
Yes, when we do resonance structure, we're delocalizing this minus charge to what type of atom? Another oxygen, which can really handle it. When we delocalize the charge here, we're delocalizing it to what atoms? What type of atom? Carbon. Carbon, carbon, carbon. But carbon doesn't like it, so it doesn't delocalize that much. This very much delocalizes. We spread the charge over two oxygens. Okay, the true structure, of course, is partial minus, right? That's the true structure of the carboxylate anion. The charge is spread over two oxygens. Here you only have one oxygen. That's what makes this. Okay, it's a little bit counterintuitive. You think more resonance structure is more stable. Well, not always. Depends on what type of atoms you're dealing with. This is more stable. The carboxylic acid is more acidic. We know that. It's called an acid. That's a phenol. But it is more acidic than this one because there's no resonance structures here at all. At least here the charge is delocalized onto other atoms, other carbons. The carbon just doesn't like being minus. With our phenols, though, we need to be able to do resonance not only into the ring, but also other groups. These are nitro groups. You'll see nitro groups in organic 2. The Lewis structure for the nitro group. Here's the ring coming off. Nitrogen. Usually double bonded to one oxygen and single bonded to the other. Within lone pairs, this would have 3 lone pairs. Nothing on nitrogen. This is minus, and the nitrogen is actually positive. So it's net neutral. Net neutral. You're not going to be able to draw it, though, without having 2 different charges. This is a nitro group. It's actually isoelectronic to this. Okay? All we did, don't write this down. If you put a nitrogen here, then that's what you got over here, right? Nitrogen double bond to O and O minus. Double bond to O, O minus. But if you put a nitrogen here, that atom is now positive. And so you end up with a net neutral arrangement of atoms, a functional group. So, that's your nitro group. Some books actually include nitro on the functional group list early on, but we didn't cover that one. You'll see it in organic 2. Okay, practice resonance structures. 2 main ways, in, out, electrons in, electrons out. Yeah. Of course, if you're doing acidity, you want to consider the conjugate bases, right? Okay. The things we talked about early on are how you do things. why we talked about it. I presented it in a certain way. So then from then on, you do things just like this. And if you recognize that there's just consistent standard ways to approach things, then it becomes easier. As opposed to every time you try to do a problem, you just have to think, no, there's systematic ways to approach things. And if you need a review, pull out your Acidbase handout from test 1. And we're bringing in more resonance. You should even look back at the resonance examples we showed back then. I talked about it more generically back then. Okay. One at the bottom. Anybody got answers to the one at the bottom yet? Golden rules of resonance. Again, free information. I tried to summarize the key points. And then on the back is a little application. Before we move to the next handout, any questions about resonance? Okay, let's look at Dienes. So this is a warm-up page. One thing we'll be seeing is that, first off, a diene, 2 enes. It's a conjugated diene. All right. React with HBr. We'll see that we can get a difference in outcome depending on temperature. That'll be something major here. Temperature. The chemistry, though, is very similar. We got pi bond, HBr. Okay, we've been reacting alkenes with H+ for a month now. We'll also be looking at a very important reaction called a Diels-Alder reaction. Diels and Alder being the 2 chemists that developed the reaction. This may be our first look at a named reaction. We have Markovnikov, that was a general description of an outcome. Typically when reactions go by a chemist's name, it usually indicates it's a pretty darn important reaction. Okay, and you'll see a number of these along the way, particularly in organic 2. So the Diels-Alder reaction, actually 2 chemists, a very important reaction, and I'm pretty sure it won Nobel Prize at some point. Okay. And we'll see things. Now we're going to focus on dienes. That is 2 enes in the molecule. But you can also have more than 2. You can have trienes and tetraenes. I mean, how many enes does a tetraene have? All right, 4, right? Okay. You get beyond 3 or 4, you start calling it a polyene. Poly meaning multiple. Okay? I mean, these are polyenes. I mean, you can count these up. What is there about? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 alkenes. Pentaene, I reckon. But these are polyenes, multiple enes. Amphotericin is a common antifungal drug. It's a polyene. Okay, because you got all these enes here. It's also a macrocycle because you got this big, huge ring. You see this huge ring here? About 25 atoms, or at least size ring. And it's got this sugar group here, sort of a aminoglycoside type of carbohydrate group. You know, functional groups, carboxylic acid, yeah. Alcohol, stereochemistry, beautiful molecule, right? Antifungal drug. Okay. Chemistry of dienes. I think it's now chapter 16 in the latest version. Latest edition, chapter 16, I'm pretty sure. Or if you have another book, look it up in the index. Dienes. Boom, there you go. It may be chapter 3 or chapter 9. Conjugated versus non-conjugated versus accumulated. We've already done that, right? It was in the other handout. Nomenclature of dienes. Here we go. Longest continuous chain. Well, it's 1, 2, 3, 4, 5, 6, 7. Right? 1, 2, 3, 4, 5, 6, 7. And both alkenes need to be in the longest continuous chain. Both of them do. But they are. It's 7. So it's hep. Right? Hep, like heptane, heptene. What we do when there's two enes is we say heptadiene. Heptadiene. If there was a third alkene in here, it would be a heptatriene. This is a heptadiene. Now we have to say, where are the enes at? What's going to be the one end? Here. 2, 4. Coming this way, the enes have the lowest numbers. So we put here a 2, 4 heptadiene, with the 2 and 4 indicating the positioning of the alkenes. Make sense? But let's don't forget to note EZ, the stereochemistry. Because these alkenes, both of them are stereogenic. The first alkene, is it E or Z? It's E. What about the second one? They're both E. So we would put E, comma E in front, in parentheses, dash. And that should be a unambiguous name. Look good? Pretty straightforward? What's the name of the next compound? The only difference is what? Same exact name. That's because these two are just stereoisomers. Same exact name, right? Everybody see it's the same exact name? The only difference is one of the alkenes, not both, but one of them has different stereochemistry. And the Z goes with the first number over here. So the Z goes with the 2, and the E goes with the 4. Okay? At the 2 position, this alkene is Z, but that one is E. So the ZE, and then the same name, 2, 4. And we know that the first letter goes with the first number. We've got 2 stereogenic sites. There should be 4 stereoisomers. The others would be what? You could have a ZZ, and you could also have a EZ. That'd be all 4 of them. Yeah? Name the other compound. What's the longest continuous chain? 6? Anybody get anything else? Yes, it's 6. The longest continuous chain needs to contain, with alkenes it needed to contain the alkene. But with dienes it needs to contain both of them. So it's pretty much 1, 2, 3, 4, 5, 6. If you went this way, you would get longer, but this way would not include that alkene. You have to include both positions to be included. Okay. 1, 2, 3, 4, 5, 6. We have a hexadiene. What's the one position? Is it on the left or the right? It'll be over here. Either way you go, the first alkene's at the 1 position. But if you do it over here, the chlorine is also at the 1 position. We have 1 chloro. 2, what's at the 2? 2 propyl. That should be all one word. Let's just erase here. Hexadiene. Just one word. What else do we need here?
1, 5.
Was that?
A 1, 5 to note our diet.
Yeah, you're right. That's perhaps why I left a little space. Yeah, there should be something else there. Between here, we need to note the positioning of the 2 alkenes. Very important. Otherwise, where are they at there? They could be maybe here and there and there. Yes, that should be a 1, 2, 3, 4. And the other one's at the 5 position. 1, 5. Hexadiene. With this 1 and 5 indicating where the dienes are at. But what else do we still need here? We need an E or Z. Is it E or Z?
Z.
E. Right? Chlorine is high priority on this end. On this end, it would be this group. Those are not on the same side, they're on opposite sides. Right? E? Are we done? Need anything else for this name?
Can I ask why is that the priority here?
Carbon or carbon?
With 2 H's.
They're the same. They're the same. Which one's out here? Carbon with H's or carbon with another carbon? That's your priority group. That alkene is not stereogenic, so we don't need a letter. This E applies to the stereogenic alkene, right? There you go. The other possibility is to have a Z form here where the chlorine would be, drawn the other way or on the same side as this group. Okay, that's nomenclature of dienes. Should be pretty straightforward. Below is really another application of dienes and polyenes. Have you guys ever heard of terpenes in biology class? Terpenes are a class of natural products, often obtained from plant materials, plants and trees. The other natural product we saw way back, test 1, was alkaloids. Alkaloids have a basic nitrogen. They thus are alkaline-like. That nitrogen is basic. Terpenes do not have a basic nitrogen, or they would be called alkaloids. Terpenes often are hydrocarbons, but sometimes they contain like oxygen. Limonene, it's found in lemons. Okay, we can be extracted from lemons and distilled, etc. And it smells really fruity. Okay, these are all natural products. Terpene or terpenoids. Okay, terpenes come originally from this simple diene, with a methyl on it. Okay, you can name this guy. It's called 2-methyl-1,3-butadiene. But it more commonly goes by the name isoprene. Isoprene. And from isoprene, the plants make these other compounds through polymerization, dimerization, polymerization. Okay? And this formula just becomes multiples. So you see, limonene is just this formula times 2. That's where this molecule came together and reacted, probably with an H+ catalyst to get some alkene chemistry going. All right. 4 of these can come together to give this molecule, times 4, taxodiene. You're getting some complex molecules. You can also get retinol. Now see, this doesn't have any oxygen. It's times 4 in terms of the carbons. 4 here would be 32. So it's sort of like it. It really has gained an oxygen and maybe lost water along the way. Maybe gained 2 and lost an H2O. So it's not exactly a terpene, but it's called a terpenoid. It's essentially a terpene, terpene-like. Okay, squalene. Squalene, fungi. What do you call them? I haven't had biology in a long time. What do you call them these days? Fungi have squalene, menthol. Beta-carotene, ever heard of that one? Down in carrots, okay? You look at the formula, it's probably 5 to 8. It may or may not be a terpene, but it's certainly a terpenoid. Ultimately, these are made by the plant starting with isoprene. Isoprene made from plant taking in carbon dioxide and chemistry getting to that point. Fascinating. Plants, super synthetic factories. Where's the one up there? Taxol. The structure of Taxol is not up there. But Taxol is a drug for breast cancer, and it was originally isolated from the yew tree. And this is sort of some of the wood. But out of that wood and out of that tree can be extracted that compound. Okay, so that was terpenes. Let's look at the chemistry of conjugated dienes. All right, there's your heading. That's where we're headed towards. 1,2 addition, also known as direct addition. If we react this simple diene with HBr at cold temperature, we can get this product here. This mechanism is nothing new. We're just adding HBr across this pi bond on the end. Now, this diene is symmetrical. We did the chemistry here or here, you get the same product. Let's just do it down here. We have H+, Br-. This alkene attacks the H+. Where are we going to leave cation at? Left or right? Correct, on the right. So we pull away. See, here's where you have to have precise arrows. First off, we don't just take an arrow and do something like this. That is not enough precision. First off, I don't know what this means over here. From day one, we either show it as HBr here and we can attack the H+, or we show it covalently and we have to break the bond, but this is not sufficient. Also, this is not sufficient. H+-Br. HBr is either ionic or covalent. It's not both. Okay? So, here, the arrow needs to mean something. These electrons need to be pulled away from this carbon Okay, so we want to grab them and pull them away from that carbon. They hinge. Somebody grab this arm and pull it up. That's what you're doing. You're grabbing it with the arrow and you're pulling it. So just doing like this, that doesn't mean anything because, so there's your right arrow. And that leads to boom, boom, boom. Okay, now this is bonded to H and the cation is here. Nothing new from what we've done. Now, Br minus added here gives you this product. And we will do that. But first, let's consider resonance here. This cation is resonance stabilized. We can draw a resonance structure. We can just move this over. And we get boom, boom, boom. So our first intermediate is a cation, but it's a resonance stabilized cation. By the way, what's the name of this cation with the charge next to the alkene? Name for this general type of cation. No, vinyl is where the, it would be here. That's a vinyl cation. We said it first thing last time. Allylic. Allylic cation, resonance stabilized allylic cation. Here's your resonance discussion. True structure is a hybrid, right? Anytime we do resonance. Okay? And from now on, we just have to know that. We can't explain resonance every time we do it. A lot of discussion right here. Resonance error. Okay? How do we get final product though? Final product comes from the Br minus attacking this resonance structure. Well, see, that's a little bit misleading. There's only one structure here. It attacks here, and if we attack there, it gives us product, right? There's a new H on the end, there's a Br, and we have done an addition of HBr. But this is a 1-2 addition. All right? I'll draw in the new H. But if the new H is at the 1 position, where's the bromine? Bromine would be at the 2. Now that's not nomenclature. That's just me saying, okay, if we call this 1, then the next carbon would be 2. And so it's a 1-2 addition. Below we'll see a 1-4, and that'll make us understand the 1-2 a little bit better. This is called a direct addition. We've been doing direct additions for a month now. We just did a direct addition to this alkene. Okay? This will make more sense when we do something that's not a direct addition below. Now, I'll look at this resonance structure one time. The resonance structure, the hybrid is boom, boom, boom. The hybrid is really this, right? Partial plus, partial plus. There's our 1 intermediate. And then the Br minus actually has a choice. The Br minus actually attacks here. Hold up now, how do you work with these hybrids? What do I move? They're cumbersome to work with. That's why we don't work with hybrids. But ultimately, you got 2 partial positive carbons. But it ends up attacking here. Let's work with the individual fake structures instead. Let's say it attacks here, but let's attack this fake structure. That's going to give us a nice product. But we know there's also a partial positive charge over here, because we know what resonance is. Okay, this is the outcome if you do the reaction at cold temperature, minus 78. Why that temperature? Because if you put dry ice and acetone, which is both commonly available in the lab, the temperature will become negative 78. Okay? If you put acetone, if you put dry ice in acetonitrile, I think you get minus 40. There's a list of these that you can get. If you put wet ice in water, I think you get like 0. All right? 0 degrees, wet ice in water. Okay. This is known as a kinetic product also, because it's formed fastest. Kinetic refers to rate. This product's going to be formed fastest, and thus always first. I'm not going to erase what I got drawn there, because let's move down here and let's do the reaction with higher temperature. If you do the same reaction but give it some heat, like about 40 degrees or higher, you'll get this product. Now first off, that's a 1,4 addition product. Because look at this compound. Where's the new H? We added HBr. The new H is here. Because that end carbon has 2, this end carbon has 3. And if we call that 1, where's the bromine position? It ain't at 2, it ain't at 3, but it's where? 4. So we say this is a 1,4 addition. The HBr is added to the 1 and 4 positions. Above that was a 1,2 addition, yeah? So, we see it's a 1,4 addition. It's also called a conjugate addition. We'll see why. Mechanism. It's the same mechanism. Same mechanism. Okay? It's the same starting material. It's the same reagent. We attack, we get this. But this is resonance stabilized. And we can show this resonance structure. We know the hybrid is really this. But instead of the Br minus attacking here, it attacks where? It attacks over here. That's the 4 position compared to the 1. Ultimately, that's 2 different sites it can attack because our cation is conjugated. Conjugated means the same thing as resonance. And because it's conjugated, that's why we can get the Br adding over here. And that's why this is also called a conjugate addition. It's another name for a 1,4 addition. Now again, we typically don't work with hybrids in our mechanism. Instead though, we can show the resonance structure, and then we can do the chemistry from the other resonance structure and say, okay, from here, if this adds here, now we have a nice structure with all these full bonds. But what does this here give? Well, then that gives that product, right? The only difference is down here we sort of invoke and use that additional resonance structure. I won't keep saying it, but again, it's just one intermediate, right? This is one intermediate. It's that. Okay, this is known as a thermodynamic product. It's not formed fastest. Thermodynamic refers to stability. It's more stable. Why is this product more stable than the above product? It has to do with the alkene. Which alkene is more stable? Top or bottom? Bottom, why? Disubstituted. The one above is monosubstituted, right? Just like we judge. Yeah. More stable. More stable, we call it the thermodynamic product. The more thermodynamically stable product. But it ain't formed fastest. Let's look over here and look at the reaction coordinate diagrams for this. They're both on the same page here. This page was actually included in the earlier alkene handout. Here's the exact reaction we just did. It's just drawn in condensed. It reacts to give the carbocation. Okay? Here's the carbocation. You get the same carbocation no matter what the outcome. They call it the common intermediate. Okay? So this is your resonance stabilized allylic cation. From there we get a difference. We can either get the 1,2 product or the 1,4 product. The 1,4 product's more stable, right? It's thermodynamically more stable. We said that. Alex told us what? So it's lower. What about the transition state leading to that? Usually we say the more stable product has the lower transition state. Is that the case here? No. If we believe this, the more stable product has the higher transition state. And back then when I showed you this, I told you that was kind of odd. And I said we would see it later. Well, now it's later. So, which one's going to be easier to form? Well, this is the easier pathway, right? Lower energy. They're actually going to go this way. It's going to be easier to form. Uh-oh. The 1,2 is easier to form. But that ain't the most stable. First off, why is this easier to form? The answer is a proximity effect. And I kind of got it right here still. Let's go back over here. Original alkene attacks H+. When this attacks H+, where's the bromine going to be? The bromine is near the H+. So the bromine is over here. The bromine is over here, near the H+. Which is it going to be able to more easily attack? Here or way over there? Here we go. I'm going to clap hands with you and you. Which one can I clap hands with? Well, he's real close. It's going to take effort to get over there. Bam, this is easier. Proximity effect, closer. To attack way over there, that's cross-country track. That takes more activation energy to go way over there. More activation energy to go cross-country. Boom, faster. Oh, we're out of time. We need to answer why with heat, though, do you get the other one? And if you look below, it sort of talks, summarizes that. Why with heat do we get the other product?